Okay, hi everyone. So welcome back to part 4 of lecture 1. And in part 4 today, we'll be going over the terminology and the loss functions and the evaluation criteria, right? So just to recap over the first 3 parts of this lecture, right? So the first part, we started with the very basics. We went over kind of basics like, vectors and vector operations and matrices and matrix operations. Then in part 2, we went over the different types of machine learning, right? So we saw that we can actually look at machine learning from a perspective of different kinds of labels or outputs, right? So we have regression, we have classification, we have ranking, we have recommendation. All of these kind of differ in terms of the label space. And we also have the different types of machine learning based on the amount of labeled data, right? So if you have either no labeled data, you have unsupervised learning, and you have kind of all labeled data, right? So all your data is labeled, you have supervised learning, and then you have something in between, which is semi-supervised learning, active learning, and so on, right? And in the part 3, we actually looked at several applications of machine learning. So we looked at applications of classification, we looked at medical diagnosis, we looked at spam classification, we looked at handwritten digit recognition, we looked at applications of regression. So we looked at house price prediction, right? And then we also looked at applications of unsupervised learning, and we looked at applications of reinforcement learning, right? So now we are actually going to go over in the fourth part, we're going to actually mostly focus on supervised learning and then study how do you exactly formulate supervised learning problems, right? So we are not going to really cover any machine learning classifier yet, but we are just going to go over the kind of broad principle of how these techniques operate, right? So we'll go over things like what is a loss function, what do we mean by evaluation criteria, right? And some basic terminology. Okay, so again, um, we'll actually start with an application of classification, right? So we'll go over the medical kind of diagnosis problem, right? So if you recall, we had 2 classes over here. One is do not have diabetes and have diabetes, right? So again, going back to our notation, do not have diabetes is basically the negative class, right? And have diabetes, say, is the positive class, right? So this is say +1 and this is -1. So again, this is a little bit of, sometimes people use +1 and 0. So +1 is positive, 0 is negative, or you use +1 as positive, -1 as negative. I don't think really it makes that much of a difference. You can kind of renormalize either way, right? But I think over here I'll just use plus as +1 as positive and -1 as negative, right? And then I have the hypothesis space. The hypothesis has a decision boundary, right? So the decision boundary is basically the part that separates the negatives from the positives, right? So again, if you recall, we had basically all of these now are negatives. So this is actually a negative instance, this is a negative instance, this is a negative instance, and this is a negative instance, right? And these guys are actually positive, positive, positive. So these actually have diabetes, right? So these are have diabetes, these are do not have diabetes, right? So these are the terminologies that we will use. Again, as we saw, all of these are features, right? So this is one feature, this is another feature, there's a third feature, and there's a fourth feature, right? So all of these are features in the model. And then this is the label, right? So this part is the label. Similarly, this is the label, right? So every instance has a feature and it has a label, right? This part is called the hypothesis, right? That we just marked. This is the decision boundary. That is the hypothesis, right? Um, and then finally, all of these are instances that I've marked, right? So essentially at a high level, I'll just go over this very quickly, that what a machine learning classifier will try to do intuitively, right? So it'll check, just like a human actually, how does a human kind of work and kind of look at these, right? So it'll look at things like the blood glucose level, the blood glucose level is 30, it is 22, 22, right? These are probably lower blood glucose levels, right? So they probably don't have diabetes. You look at the body mass index. I think the blood glucose is actually a very important feature, but you look at the body mass index, again, the body mass index is kind of high, right? The body mass index is actually normal here, right? And then you look at the BP also is normal, and probably the age, right? But of course, age is not as important a feature, but maybe if one of the numbers is on the higher side, for example, the blood glucose is on the higher side, but the age is less, right? Then probably the person does not have diabetes. So I think in some sense you can think of these very naturally as a tree, right? And in fact, it's not surprising that a decision tree is actually one kind of machine learning model for kind of classifying between classes. But you can also think of that a model essentially looks at these and automatically learns how to kind of segregate between these different values, right? So there's no magic going on, it's just math underneath, and essentially based on the math it is trying to make a decision whether to basically put it in a positive class or a negative class, right? You look at the negative, I mean, you look at the positive cases, you see all of the blood glucose levels are higher, right? And now there is one case where the blood glucose level is not that high, right? But you see that the BP is actually high, right? So the BP is high, and the body mass index also is slightly on the higher side. So I think, so in some sense, this is one more notation which is important, is the training examples, right? So the training examples, basically all of these are training examples. So the training examples is what the model sees when the model is being trained in the training phase, right? And in the testing phase, we'll actually give kind of unseen objects or unseen instances for the model to classify, right? So just kind of looking at the terminology again, I define these as training examples. So basically X will call as a feature and Y will be a label, right? And there are several instances of this. So there will be basically X1, Y1 up to XM, YM, right? So this is the training instances. And of course, kind of critical thing about machine learning is that we don't want to overfit, right? So we don't want to kind of memorize the entire training data, but rather we actually want to generalize, right? So the whole goal is that I don't want to kind of memorize my training data, but given an unseen test data, right? Test instance, I want to be able to perform well on my test instance as well. So this is a single training example, and then the training set, right? So this actually is a training set over here. So I'll just call this training set, right? And a training set typically is a set of instances drawn from a distribution, right? So I think one more key assumption is that there is an underlying distribution which we don't know about, that basically P of XY. So it's a joint probability distribution that essentially draws these samples. And again, I mean, we'll actually go over probability in more detail in the next couple of classes, but just kind of understand that there is some kind of underlying joint kind of ground truth distribution that generates these P of XY, right? I think one more key assumption made by many of the models is basically called IID, which is independent and identically distributed, right? So the data points, the training data points are assumed to be all independent of each other, right? And they are identically distributed. So they have the same underlying distribution and they are independent of each other. So this assumption basically helps us to then model and kind of define loss functions for these. Okay, so the target function is the true mapping between X and Y, right? So that means that given a X, there exists a F star, right? Such that F star of X equal to Y, right? So for all the points in my training data, I have over here that yi is equal to f star of xi, right? So that means that there exists an f star, but obviously since it's a machine learning problem, I don't know this x star. I mean f star, right? So I don't know this f star, and I want to find this f star, right? So the hypothesis function, the hypothesis is actually a function that is considered by the learning algorithm, right? Which is similar to the target function. So that means that I'll call this h, right? So I want to learn a h such that f star of x is equal to h of x, right? So f star of x is basically equal to y, right? So this is equal to y, right? So I want this to be equal as much as possible. And h, typically over here, h, which is the hypothesis function, would actually be some kind of assumption, right? So I make some modeling assumption, right? And based on my model, I have a hypothesis space. And we'll actually look at different modeling assumptions. So like one simple modeling assumption, which actually is a modeling assumption, is that the separator is actually linear, right? So this basically is, for example, the hypothesis function, right? H of x, and the assumption is that this h of x is linear. So we shall actually see this in the next couple of classes. So this region, for example, when it's positive, we can say this region corresponds to h of x being greater than 0, right? And this negative corresponds to h of x being less than 0. So we'll actually see this in more detail, but I'm just kind of giving a kind of a preview into what we'll be seeing soon. So this hypothesis function is actually linear, and we are assuming, right, that the separation between these features is linear. It may not be linear, right? So again, in every machine learning model, we'll be making an assumption of the hypothesis space. And I think it's important to understand what this assumption is. Okay. Another important terminology is the test set, right? So we'll be assuming that we have an unseen. So I think the critical point over here is that this is unseen, right? Unseen to the training data. So we have an unseen, not seen by the training algorithm set of data points, which we'd use to actually evaluate the p of xy. I mean, sorry, basically evaluate the h of x, right? So it evaluates how good h is, and we'll see some kind of evaluation criteria as well, that how do we evaluate these instances, right? And finally, we have the hypothesis space, which is the space of all the hypotheses that can be in principle be considered for returning the algorithm, right? So that means that the hypothesis space is essentially the space of all the functions h that can be learned, right? So I'll just write this down over here, space of h. So for example, when I consider the space of linear models, right, when I know that my decision boundary is linear, I'm assuming that my hypothesis space is actually linear, right? All right, so what's the supervised learning workflow, right? So the supervised learning workflow is that I have training samples, right? And then my training samples, basically, I have this underlying distribution P of XY, and then I generate my training data set, right? So it's M data points here, M data points. And just recapping, right? So I have this as features, I have this as labels, right? So I have M data points, and I give this to a learning algorithm, right? So the learning algorithm basically takes my training data, and it essentially outputs this function f, right? So this function is my, in some sense, learned function. Okay, so this is my learned function. And finally, once I have basically learned this kind of function f, right, I have my test data points, right, xt, yt. And essentially, given my y hat, so y hat is my predicted value, right? So y hat equal to f of xt. So I'll call this y hat t, right? Just to be clear, y hat t is f of xt. This is the predicted value, right? So then I have a loss function L that basically gives me that how good my predicted value is, right? So based on this, I have many test data, and given a lot of test data, I can actually evaluate my algorithm. So if you must have heard the accuracy, right? What is accuracy? Accuracy of a machine learning algorithm. Accuracy means that I have a lot of test instances. On my test instances, I actually evaluate the resulting model F, right? So I evaluate the resulting model F, and then the resulting model F, I get a number that it's 80% accurate, right? It's 85% accurate. So this is what we can evaluate on this test data set. So this is called kind of evaluation, the evaluation workflow. So so the supervised learning workflow consists of this training process, right? So basically all of this is the training process, right? Until I get this F. And in some sense, all of this here is the evaluation process, right? So this is evaluation and this is training. Okay, so these are the two critical pieces in machine learning. I first train and then I evaluate and then I test how good my model is performing, and I can possibly kind of repeat this multiple times until I get the desired accuracy that I care about, right? So again, training examples, x1, y1 up to xm, ym. Okay, so now exactly what is the learning algorithm, right? So learning algorithm assumes that there is a certain loss function. Okay, so this is the loss function over here. The loss function L essentially tells us how good my predicted value is y hat, right? So y hat over here is the predicted value and y is the true value, right? So it compares the predicted value and the true label. I mean, no, not value, it's a label, right? So this is a predicted label and is a true label. So over here, f of xi is my predicted label and yi is my true label, right? So what this means is that this objective, when I'm minimizing over f, this is actually called an optimization problem, right? And the optimization problem is where I actually minimize over the space of all my f's, and I solve this problem. So it's a sum over I from 1 to m, L of f of xi, comma yi, right? And obviously given certain structure about L, right? So if L is, for example, continuous, L is convex, if I know some additional structure about L, then I can actually kind of optimize this efficiently. So there exists kind of algorithms to optimize this, and we'll actually see this in the next couple of classes, right? So the important questions over here is that so I think the kind of machine learning design questions is how do I pick L, right? So this depends on the ML algorithm, right? And the application. And the second is what is F? So I think these are two critical questions, um, which basically, and again, I think this F is the model, right? So F is my model and L depends on the machine learning algorithm that I use, right? So finally, of course, the third piece is how do I optimize, solve this problem, right? And this, by this, I mean the problem over here, which I've highlighted, right? So first is how do I pick L? What is F, right? And how do I solve this optimization problem, right? So I think these are the three very, very critical aspects of machine learning that we need to understand, right? So finally, I think this is all kind of um, the training process, right? And finally, we come to the evaluation. So the evaluation involves testing, right? So given a new point, unseen point is important, super critical, right? Given an unseen point xt, yt, I can get y hat, right? And then oftentimes I have an evaluation criteria. So I measure the error, right? So by the way, oftentimes the error here can be L, right? L can be used to measure the error, or it can be something else, right? So you can use L, y hat, t, yt, or it can be a new form as well. Oftentimes what happens in machine learning is that L is what is known as a relaxation of the true error, right? Because it's oftentimes not possible to optimize the true error. We actually kind of relax the problem to make it easy to optimize, right? So L is not exactly the final measure, like the accuracy that we care about, right? So however, when you are evaluating, we actually use the true measure of accuracy. So we'll use the error, for example. Okay, so far so good. So we have the training process, we have the training algorithm, then we have the testing process, and we have the evaluation. Okay. So, all right. So now let's very, very quickly look at exactly how do we do this um, in certain cases, right? So for example, linear regression. So we start with linear regression. Linear regression, again, if you recall, regression is where I have my features belonging to R raised to D, right? So they are D-dimensional features, and I have my ym to be my label, which is a continuous value, right? So the hypothesis space over here basically is defined as the set of linear functions. So it's A transpose X plus B. So right, so basically A transpose X is exactly A dot X, right? So if you recall, we saw the dot product actually, right? In the first lecture, in the basics, we saw what the dot product is. So this is exactly the dot product, right? So essentially f of X is A dot X plus B, okay? Now, the reason why this is called linear regression, right, is exactly because the hypothesis space is a set of linear functions, right? So these are all linear functions. So A is a vector in R raised to D and B is in R, right? So in some sense, so this particular process is also called parameterization, right? So this is how we have parameterized this is how we have parameterized the model in the case of linear regression, right? And A and B are my parameters. Okay. So over here, when I was saying minimize F, what I really mean is that I'm minimizing the parameters of F. And we'll actually see this in the next class when we'll actually go over linear regression in more detail, right? So now in the case of linear regression, I think the simplest form of error metric is actually just the square distance, right? So f of x is a dot x plus b, right? So it's a continuous value, and then I have my label y. I can define L of f of x comma y as just a squared error between f of x minus y square, right? So essentially I have the value of f of x, I have the value of y. So for example, if f of x is 23, right, whereas my label is 25, the difference between these two is 2, right? So this value would actually be 4 then, right? The error would be 4. So as you can see, the closer f of x is to y, the lesser my error is, right? And if you recall this problem, we were actually minimizing L, right? So the goal is to basically parameterize A and B, right? So concretely, we'll actually see this in the next class, but I'm just kind of giving you a primer, right? So sorry, I'll just move this a little bit to get some space. So just making this more concrete, the optimization problem will be minimize A comma B, right? A dot X plus B, actually Xi minus Yi square, right? And actually I'll move this a little bit, okay? So it's minimize the sum of I from 1 to M. So I have M training data points, A dot Xi plus B minus Yi, right? And I'm solving for A and B. So A is a vector in R raised to D and B is a scalar. So this problem is actually called optimization, right? So this is the optimization problem that I want to solve. So just keep this in mind. We'll actually look at this in more detail in the next class. Okay, so this is the error metric. And finally, okay, so finally, guys, this can also be the error metric, right? Because once you actually optimize this and get A and B on the test set, right, I can use the same L, right? And I know what is the, in some sense, the L2 error of my model on my data set. Okay. So what does linear regression do? Well, I have a set of points. Linear regression tries to find straight lines, right? So essentially in the end, there will be one straight line that will be basically be optimized, right? And each straight line corresponds to a unique set of values of A and B, right? So there'll be one unique straight line that can be obtained given my data. Okay. All right. So we can do the same for linear classification as well, right? So we saw very, very briefly linear classification. So I have a, so if you recall the kind of medical um, data set, right? For diabetes, we have a set of positive points and then we have a set of negative points, right? So if indeed my data is well separated like this, then what I will say is that I have this one kind of decision boundary, which basically is my hypothesis. This is also called decision boundary, right? Or it's called separating hyperplane. For in the case of support vector machines, we'll actually see this as well, right? But I think for now, we can just treat this as a decision boundary. Okay, so it's a decision boundary. And essentially, given these positive points and these negative points, we want to find the hypothesis space, right? So again, the set of points here are x1, y1 up to xm, ym. In this case, xm is my feature vector, right? But ym actually belongs to 0 to k minus 1, right? So what I drew over here actually is k equal to 2, right? So this is just binary classification, but you could do this for multi-class classification as well. Okay, so then you have the hypothesis space, which is a set of linear functions of fx equal to sine of A transpose x plus b, right? So this is critical. So in linear regression, f of x was just A transpose x plus b, right? But what I mean by sine is actually depending on whether the value is greater than 0, then it's plus 1, otherwise it's minus 1, right? So I'll just make this very clear. So f of x equal to plus 1 if A dot x plus b is greater than equal to 0, and this is equal to minus 1 if A dot x plus b is less than equal to 0, right? So this is exactly what we were seeing, that this region corresponds to f of x. So if I call this f of x, right, which is basically A dot x plus b. Oh, sorry, this is not A dot x plus b. A dot x plus b is actually the linear function. F of x, so I'll just actually erase this. So this region corresponds to A dot x plus b greater than equal to 0, right? And this region corresponds to A dot x plus b less than equal to 0. Okay, so this is my function f of x, which is sine of A x plus b. Okay, and finally, the error metric is actually the accuracy, right? Or you could also use more complex, something more complex like AUC. But for right now, just think of accuracy, right? So what is accuracy? Accuracy just measures the number of correct predictions that I have, right? So assume I have 100 test data samples and 80% of the times I'm correct, 20% of the times I'm wrong, the accuracy is 80%. Okay. Now, this is one case again where the error metric is actually different from the loss function, because it turns out that accuracy is not something easy that I can optimize, right? In this case, I had the squared function, right? And it turns out this is easy to optimize because it's a continuous function. This is not the case in the in accuracy, right? So I have this function, which is f of x, and this is no longer that easy to optimize. So I need to actually use something called a relaxation, right? And that's where different machine learning algorithms come in. So I have the log loss, which is basically logistic regression. If you have heard of logistic regression as a classifier, that corresponds to a log loss, right? A hinge loss is support vector machine, and perceptron loss is basically perceptrons, right? So these are different machine learning classifiers, and each of these correspond to different versions of loss functions, which are all relaxations, right? So all of these are basically relaxations of accuracy. And we'll actually see this also in the next few slides. Okay, so again, linear regression, this is basically A dot x plus b, say greater than equal to 0, and A dot x plus b less than equal to 0, right? Multi-class classification is a little bit more complex, so I won't actually go into detail right now. But the simplest way of doing multi-class classification is actually by doing it in a bunch of linear classifications, right? So I have one kind of model for this, right? So these red points correspond to one, um, basically say this corresponds to A1 x plus B1. Okay, so essentially what I do is that I try to classify first the red versus everything else, right? So the red become the positive, and the green and the, I mean the triangles and the square, the cross becomes a positive, and the triangles and the square become the negative, right? And then I train one decision boundary like this. So this I do first, right? Then I can repeat this. Then I consider basically the then I consider the triangles as positive, and then I consider the square and the crosses as negative, right? And finally, I can consider the squares as my positive and the triangles and the crosses as negative, right? And I train a third model. And in some sense, you can think of these as combining these different three models. So this procedure is called one versus rest, right? So this is one way of doing um, basically multi-class classification. There are actually a few others as well. So we look at this in more detail later on. Okay. All right. So I think this is critical. The binary regression operates on a continuous set of outcomes, right? And in the case of binary classification, we just have basically the outcomes being +1 or -1. In this case, actually, I kind of called it 0 and 1. But if you're getting confused, just think of this as -1 and think of these as +1. Okay. So these are the features, and this is the label, right? So again, this is actually getting a little bit more detailed. I won't actually go into this as much, but again, these are the features, and this is the label, right? And the whole point is that I'm given my training data, right? So my training data, for example, comprises of these 4 data points, right? So I have 4 data points for training. So if I want a hypothesis H, which is consistent with my training, right? Okay, so note that there are 8 possible configurations over here, right? So say if you assume that x1, x2, x3 are just binary, so 0, 0, 0, 0, 0, 1, 0, 1, 0, etc., right? So there are 8 possible values of this, right? And given these 8 possible values, it turns out that there are 2 raised to 8 possible functions, right? Why there are 2 raised to 8 possible functions? Because for each configuration over here, I can have 2, right? So similarly for this, I have 2, right? And so on. So for each of these, I have 2. So there are 2 multiplied by 2 multiplied by 2, 8 times. So there are 2 raised to 8 possible functions. Okay. But I have in my training data, I have actually given values for 4 of these cases, right? So in the training data, I'm actually given values for 1, 2, 3, 4. Right? So that means that I only have actually 4 possible choices now that I need to fill, right? So there are only these 4 choices that I need to fill. So that's why there are actually 2 raised to 4 observations that are consistent with the observation. So that there are only 2 raised to 4, 2 raised to 4 possible functions out of the 2 raised to 8 that are consistent with my training data, right? So the whole point of machine learning here is that I want to be able to choose the best ones, right? And of course, the second question that actually is important is that what if my observations are noisy, right? So maybe it's possible that the 0, 1, 0, 1 that I have in my training data actually has some noise, right? So I think when we are thinking of the kind of designing machine learning algorithms, it's basically important to think of all of these aspects as well. Okay, so very quickly, some challenges in machine learning, right? So how do we choose the right hypothesis space, right? So the kind of critical aspect over here in kind of influencing the decision of picking the right hypothesis space is basically the difficulty of learning over the chosen space and how expressive the space is, right? So in some sense, these are kind of at odds with each other. One is basically trying to minimize the difficulty and basically learn the simplest explanation, right? So the simplest explanation, and in some sense, there is also the thing that I wanted to be expressive. so that it's rich enough, right? So I want it to be simple, yet I want it to be rich, right? So rich so that it's not too simple, right? But at the same time, I don't want it to be too complicated, right? So I think it's important to keep these two. So in some sense, machine learning always tries to balance between these two aspects. Okay, so essentially this is what the kind of critical aspect is, right? So how do I evaluate the quality of our learned hypothesis? So it's kind of always better to prefer simpler hypothesis, right? So I don't want to overfit. So in some sense, the critical aspect is I want to generalize to unseen data, right? So the more complicated the function is, I will try to memorize my training data in some sense, right? And then I won't generalize as well. So that's why it's important for there to be simplicity, right? That's why simplicity is important. But at the same time, I don't want to make it too simple as well. Okay. So in terms of hardness, right? The critical piece over here is that how easy is it? How easy is it to optimize over my hypothesis? Right. So if you recall, we actually saw that we parameterize the model and then we have a loss function, and then we are trying to optimize the loss function, right? So if I just do the error, for example, like the 0, 1 loss, right, or the accuracy, it turns out oftentimes that the accuracy is NP hard problem, right? So that's why oftentimes in real world we actually look at relaxations, right? So we look at relaxations to make it computationally tractable, right? And the second aspect is we also want to have scalability. So I want to be able to scale to very, very large scale data sets as well. Okay, so with this, actually, I'll end the first lecture. So again, thank you so much, and see you for lecture 2. Thank you.